Hi, everyone. Welcome to this week's DeSci Labs community call. It is currently November 21st, and we're going to be talking about big data and academia. We'll be giving a dive into some of the problems and challenges facing scientists who hold big data and some of the potential solutions coming out of the Web3 stack. Just a couple quick housekeeping announcements. As always, if you are interested in joining the Node Stewards program, we are actively looking for people to help highlight beautiful, reproducible pieces of open science. So please talk to Carl, talk to John on that if you have any questions. I think the Future of Science seminar podcast from Gideon Nave has just come out, if I'm not mistaken, Carla. And potentially a couple other pieces as well, if you want to just give a quick update on that.
Sorry, I missed the first part. But the podcast with Gideon is coming out probably later today, maybe tomorrow. And then we have a couple more interesting podcast episodes coming out soon. We did just publish the recording of the seminar with Eric Schultz on the FAIR principles. If you're interested in that, that's on YouTube.
Okay, awesome. Thank you. And for anyone else looking for more information on the YouTube or on the FAIR data principles, we also published a community call about them from last week. And with that being said, unless Chris or Philip, y'all have any updates to give, I think we can go ahead and get kicked off with the topic of today's call, big data and academia.
Yeah, great topic. I think it's a very important topic because we all agree at the end of the day that if we're able to share data more efficiently between scientists, laboratories, and different stakeholders that are involved in the discovery and collection process, that we can essentially accelerate discoveries. Now, there's technical challenges around data storage and accessibility, and I think a lot of them can be placed in essentially three different categories, right? So there's an incentive problem. That's one. That's the human factor. As we'll see in this discussion, the human factor is somewhat subordinated to the technological infrastructure. Another part is technology, specifically that has to do with costs. All right, so storing large amounts of data and making it available is something that can become extraordinarily costly very, very fast with the current cloud architectures that we have. And finally, there's a component about, how do you make data part of the scientific record, and how do you ensure that the credit attribution system actually rewards you for posting your data, and what's the type of infrastructure that would allow not only accelerated reuse of data, but also being able to demonstrate that the types of data that you've generated with your research has actually contributed a lot of value, and therefore should be deserving of the type of honors that could allow you to accrue various types of funding and recognition within your community. And that last part is really linked to the first part, which is the incentive and human problem. If we want to dive a little bit into this, there's quite tricky incentives with matters of sharing scientific data. It's true that some communities do it very eagerly, others less so. And there's multiple reasons for that. One of them is that you essentially, when you spend a lot of your grant money to collect a expensive data set, well, you tend to think that it's essentially like a mine, like a vein that you want to mine with as many types of discoveries and papers you might be able to produce from that data set. And that if you make it available to your community, well, what you're essentially doing is making it available to your competitors. What does that mean? Well, that means that they will be able to essentially mine more credit out of it than you. So people have, an incentive to just keep that data closed and make sure that their lab will be producing as many discoveries from those data sets as possible, as to avoid getting scooped, because that's how credit tends to function. So of course, this brings us to the question. It's like, okay, this incentive problem wouldn't necessarily be present if we had a way to reward people that actually create these valuable data sets that are that are then used and leveraged by other groups to produce new discoveries. And that I guess is very much has to do with a human and technological factor. And there's another problem we haven't really mentioned. It's the matter of data accessibility. So communities that tend to not want to share their data very often have good reasons to do it because of the difficulties around, let's say, components that lead to unfair credit attributions. And there's then another very valid reason not to be sharing your data is that you're unsure that you're actually allowed to do so. And the problems around data sharing are most acute in communities that actually have data that can be shared in the open. I mean, it's quite noteworthy that in the medical community, for example, it's very well known that it's quite difficult to share data between research groups. There was that really interesting measurements or statistic that essentially says, like, for all, this kind of like random sampling of these papers that says data available upon request. And the question is like, well, what's the response rate? Like, how available is the data upon request? And I don't remember exactly the source of that result, but essentially it was something like less than 9% actually made the data available. And so what it really means is data is not available upon request. And sometimes there's very, very good reasons for that. But many times it's just a matter of UX. Essentially, the researcher has moved institutions, the data is sitting on a hard drive somewhere in the archive of some university, just getting access to it, putting it online. All of that is just a massive, massive amount of effort. And at some point, you kind of tend to lose track of these things as professors, students, postdocs, they tend to move between institutions and research groups around the world. So it's very quick. There's essentially a point where data stops being available just because of the natural loss of access to the physical locations of these data sets, which tend to lead to like enormous user experience problems. And so these are some of the really, really hard problems. And then we have another population that tends to produce enormous amounts of data, right? And here we can talk, for example, about light particle physics, cosmology, environmental science, earth science. These types of fields tend to generate, massive amounts of data. Very often these are so-called 3D data, so they have a temporal dimensions, they have their imaging data that are very, very feature rich and difficult to compress, and that leads to big challenges at the level of storing that data. And it leads to even bigger challenges when it comes to sharing that data and making it available to their community. We're talking scales of data sets that you can't just download in your local environment and run your little Python analysis scripts on that data. It's just not going to work. It's essentially big data, and that big data needs its own tools to be able to be processed and analyzed. And one of the ways that is most efficient when it comes to handling big data is essentially, well, you want to bring the compute where the data is. And that's something cloud providers like AWS will allow you to do. So you can store a petabyte of data on AWS, run computations on it, orchestrate all of this through clever use of Kubernetes and other scaling solutions. You might use some of these big data frameworks in order to be able to analyze and process that data, like MapReduce and other types of systems. The big problem with that is now you run into terrible user experience. And there's a reason why there's a profession called, data engineer, big data engineer, is that converting a simple Python script that goes and runs, the average of some measurement. For example, the typical example is average house prices. This is a very, very simple NumPy transformation. If you try to do this on a giant data set on Hadoop, well, all of a sudden, it turns out into 50, 100 lines of code that for the most part can be quite cryptic, especially for scientists or someone who's not deeply specialized in big data analytics, right? So that's another big hurdle to overcome. the ability to run compute jobs over the data without being an expert in specialized big data handling frameworks and systems is a big challenge. So at the end of the day, the question is, well, hey, okay, we have these challenges. We have the problems of extraordinarily large data being generated. We have the problems of bad UX for working on that data. We have the issues that are linked to incentives in science. We have the issues around credit. We have problems around reusability and high quality annotation of that metadata to make it reusable. What could better solution look like? Right? And I think that's really one of the core things that we're trying to explore and improve with the products that we're building at DeSci Labs. And one of the ways to think about it is, well, first of all, what type of tools are scientists used to in their daily workflows, right? How do they operate on a daily basis, right? Some scientists, use Git, others just don't. A lot of scientists will use cloud storage solutions like Dropbox or Google Drive, these types of things. So they have familiarity with a number of these tools that are very, very simple, that have good UX. And the question is then, well, what could it look like to create a better type of data publishing experience for scientists that is not only provides better reusability of these artifacts, but also does it in a much more cost-effective way. And this is where I think we can really, really make a difference. You can imagine that right now there are systems that offer decentralized storage solutions, like some of the solutions that Protocol Lab is building on top of IPFS, like Filecoin, who have quite tremendous advantages in terms of costs. So we're able to create much more competitive markets that do not rely on brand in order to store data, but rather create free markets where you have proof of data storage that is computed in order to bypass the need for essentially legal agreements that guarantee that the data is stored, because you have a cryptographic proof that the data is indeed stored and that copies are maintained across the globe to create redundant storage systems. And so that allows us to create a more free market economics, which pushes the cost of data storage down. And so that's one of the fundamental pillars, is that we can now create more efficient markets that will allow us to push the cost of data storage down. And why is this important? Well, 1 petabyte on AWS with reasonable usage in terms of download rates is about $500,000 a year. And that's absolutely unjustifiable, for most research group and laboratories. It's simply too much money, and they would much prefer spend that money in having more staff on hand, more postdoc, more PhD students, investing in research projects and all of these things. So for institutions, it becomes quite a hurdle to overcome. So that's one thing. So we can dramatically reduce the cost of storage data. The second thing is, well, storing data is just one part of the problem, right? So you have already, you have storage providers that go out there. And I think, in the scientific community, you have data that from the Atlas project at CERN that is stored on these decentralized systems. You have other research labs at University of Berkeley who are storing their data on these decentralized systems as well. But that's only one part of the problem. The second part, after you store the data, is like, how do you make it available to your community? And how do you make it part of the scientific record? And how do you allow it to accrue credit? And how do you make it easily reusable, right? So you could think of that entire part as a layer that happens on top from the decentralized storage solutions that essentially integrates the data with the scientific record in a meaningful way. And that goes beyond just, going on DOI.org, getting a DOI and slapping that next to a CID and essentially saying, it's done, it's part of the scientific record. That's not enough. You need things like metadata. You need high quality metadata to make your data reusable. And this is where, FAIR principles come in again. But I think beyond that, just having high quality metadata that's searchable, that allows other communities to be able to find that data easily, is very, very important. And so we have a number of affordances that we have to create in order to make it attractive or more attractive for scientists to store their data. At the end of the day, no single scientist on Earth wants to run their own data centers, and many are forced to. And there's quite a significant amount of money that goes into compute and storage infrastructures in many big research labs and research consortiums. I believe the CERN, is storing enormous amounts of data, for instance, on their local storage solutions, and it gets quite unwieldy and difficult to handle. So the second part, after you now have that interface to the scientific record, and you have mechanisms to accrue credit, is that you might want to think, okay, well, now that I have this, I want to make my data easily reusable by my colleagues. And what's the easiest possible way to do this? Well, for small and average data set, it's probably just a direct download button. That helps. Or you can do this via CLI. You could even think of cases where you can import data via your CLI in your Python interface. If you're using Python or other types of programming languages, it might be possible to do something like this in MATLAB and different in R as well. But you'd think, well, the next stage, if the data is big and unwieldy and start reaching, maybe 10, 20, 100 terabytes, you might start to think, well, maybe I actually want to put the compute where the data is, because data has gravity, right? It's very like data egress and ingress, which for those that don't know, this is the moving data around in and out of different locations. Is very, very heavy and very costly because that costs actual bandwidth. So how do you get around that? Well, ideally, you want to have compute nodes, CPUs and GPUs just sitting right where that data is. And then you want to be able to send, a compute job on that data that would give you an output. So you can essentially transform that data and use it actively in your workflow in order to be able to produce new scientific discoveries. This is where projects like Bacala and other decentralized compute solutions really come in. It's very, very interesting to use IPFS and content addressing as a way to operate on that data. So for instance, you might have a CSV with house prices around the world, might have, billions and billions of rows. Let's say you have all the histories of sales of houses, right? And it's an absolutely ginormous data set. It's very, very hard to operate on that data set locally on your computer due to, of course, the types of limitation you might have in RAM and GPU, CPUs, all of these things. So you need a supercomputing cluster. Now, downloading that data, putting it in your institution's supercomputing clusters is also going to be a massive pain, right? So ideally, the simplest thing you can do is program a job and then essentially use that hash and then add that hash to the job that you want to execute on and have, an output that would be able to track the output from that compute job. So you want to have tools, to be able to inspect it, to run other jobs, to essentially make it part of your workflow. And I think that's a really important. That would be a really important way and powerful way to accelerate progress in research. If you could think of like having, this vast dataverse of data objects where scientific communities can come together and have kind of a, multiplayer experience where they can run compute jobs over that data, crunch it, create data outputs that are accompanied with metadata that tell others what type of operations have been made, so that you don't need to redo it again. And that's also, environmentally very friendly. Like, for example, imagine you have satellite images and you want to grayscale it. Well, odds are someone else has already grayscaled that data set. And if you go, with metadata, you might be able to automatically, if you want to run that new compute job of grayscaling, it might be possible to automatically say, hey, wait, in our metadata, there's actually evidence that this type of job, the exact same job you want to run, has already been ran. And here's the output. Here's the hash that tracks that job. And so all of a sudden, now you don't even need to run the compute job again. So you're not, wasting computing power, since we already have the output of that previous job. Now you can take this job and essentially, run whatever other computation you want to do on top of it. So that essentially would allow scientific communities to create like this growing library of compute job outputs accompanied with rich metadata that would allow them, to create new knowledge, to discover new facts and properties about the universe. Could be very efficient. And ultimately, that's one part. The other part is like for how about for all the scientists that are not computationally savvy at this level, who aren't experienced in running these big compute jobs on large data sets. Well, what you essentially want to do it is make an experience that's as similar as the tools that they use on a daily basis. So like we've heard from journal editors that this something I heard once, from a top journal editor said, yeah, well, there's a bunch of scientists, when we ask them to share our data, they send us a Dropbox link. And, it's like, what am I supposed to do with a Dropbox link? Like, that's not helping. It's just a bunch of files. It's a total mess. I'm not going to curate this for them. There's no way. I mean, this is not included in my APCs, right? This is the big problem for scientific publishers, that there's no business model for publishing scientific data. And so what happens is that they don't want to deal with it. And scientists, they don't want to go on their whatever repository and go through the long, lengthy UX of like uploading these data sets and these systems that are essentially, that don't necessarily offer, a best-in-class type of user experience. So the question is like, well, how can you like make systems, that emulate the behaviors and the properties of these tools that people are already used to, that they figured out, and that they're essentially, they like to use, right? So you can think of how great would it be if behind archive, every paper had a Dropbox, right? A Dropbox that essentially has not only metadata associated with every file, but PIDs, persistent identifiers, associated with every file. You can't do that with the DOI system, because you're not going to be generating a million DOIs for every data set posted. But you can definitely do it, with the types of decentralized persistent identifiers that we're developing, which are essentially file paths, where you could typically say, my PID / my data / measurements1.csv, and that file path itself is a PID. And so now all of a sudden you have the ability to have extremely granular types of citations possibilities. And more than citations, you have much more higher interoperability, because all of a sudden you can import, provided these data sets aren't giant, right? If they are very, very huge, then you should definitely use that compute solution, compute over the data. But if they're not giant, you might be able, we might be able to create packages so that you can import these data sets directly in your IDE as you're working. So you could essentially, you're in your Python IDE, you're crunching data, you want to download this new data set and link it to an existing data set you might have. Well, you could just like import it directly in your IDE. With a PID, and that would provide the type of workflow experience which would be a tremendous addition to what we have today in terms of reducing the pain of reusing each other's data. And finally, there's the matter around data that's not publicly accessible, that requires authentication to reach out. And I think this is the more tricky topic, because as soon as you're talking about human data, then there's all sorts of regulations that, for some of them very, very well conceived, other less well conceived, that are there to safeguard human data. And the question is, well, how do you create, robust authentication systems to access these data sets? And I think this is a very common problem. Is like, well, it's a data available upon request because it's human data. It's a kind of a convenient cop out to sharing your data. Ideally, you'd have systems that says, well, the data that was used in this specific study can be accessed here. These are the rules of access. These are people who have the authority, the rights to access that data. And you'd essentially have a record that provides, a permanent or semi-permanent, or at least persistent, linkage to the data center or the access service to that data set, such that it's very, very, very clear how to get to that data if you're not the authors, without having to go through the loop of please contact us. And I think that's something that's very, very fundamental, and it's often quite missing. There's quite a big neglect or blind spot when it comes to accessing restricted data sets. And finally, the question of incentives. I think that's a really, really big one. You could think of an example I like to give. It's like, well, if producing a paper out of my data gives me 10 credit points, and having my data reused by a competitor group gives me 1 credit point, well, then I'm not going to make my data available. I'm going to keep, milking my data set, so to speak, and making it available 10 years down the road once I'm really, really sure there's nothing in there that's left for me to mine out. And the problem with that very often is that by the time you're not interested in your data set anymore, you kind of like, you lose interest to even share it because there's not that much interest in your scientific community to use it anyway. So you start entering the kind of like data depreciation cycle. On top of losing that data, you lose motivation to post that data and so on and so forth. So the question is really, how could we like re-incentivize sharing a research artifact? I mean, posting your data and having another group discover something of that data and create a valuable contribution to the scientific record should be something that is really highly valued, because you've tremendously accelerated the progress and the progress in knowledge generation. And I think it's right now the fact that there's problems around even things like citation fragmentation. For those that don't know, it's essentially, you have a data set and you have your paper, they both have different DOIs, you have even then a preprint. And so your preprint is gathering citation, your paper version of record, quote unquote published works gathering citation, your data is gathering citations. And it makes a mess. Because ideally, as the scientist, you'd like all of these citations to accrue to the same object. You don't want these things to be shared across all of these different PIDs. You want one PID to be accruing credit for all of the generated artifacts. And so that's a problem. That's quite inconsistently handled by Google Scholar and Scopus and these other indexers. And so what you really, really want is a way to get credit at the level of the research object and not at the level of the DOI. And that's tricky. That's tricky because the current architecture for the scientific record does not tend to facilitate this. So what that means is that the current way that we treat persistent identifiers and the current way that we treat research artifacts tends to naturally just lead to citation fragmentation. And that's a property of the system, and it's very hard to fix because that's how the backend works. Of course, you can think of all sorts of patchwork solutions that come on it. You can think, oh, we're going to ask Crossref, the metadata service. We're going to essentially index all of the different DOIs in that Crossref record, and but at the end of the day, these things don't really work really well. And as we all know, the state of metadata and PID, the so-called PID graph, is quite dismal for the time being. So what you want is a different system. What you want is a system that's simpler to use, that allows you to accrue credit to that data object. That ultimately, it should create the type of credit assignments to the original creators of the artifacts, which is something that essentially provides an incentive that is comparable to the incentives of mining that data for yourself for longer. And I think, especially at the bootstrapping phase of a system, these incentives should be even higher. So you want to create systems, that tend to address the blind spots of the current scientific record, and then you want to over-index on that so that you really kind of gather, you really kind of provide value to that specific population, which is not being well served by the current system, in a way that creates a lot of incentives for data reuse, for interoperable research exchanges of digital artifacts, such as code, such as data, such as all of these different things. So I think that's really the go. And now, the value prop, once you start combining, better system of credit accrual, better PID systems, much cheaper and cost-efficient solutions to store large data sets, and the ability to run compute over the data and to run compute jobs in interface with your publication system that as well gives people the experience that is reminiscent of tools that they know, like Dropbox and Archive and these things. Then you're really into the providing value to people's workflow. And I think that's really the goal here. And especially insofar as it allows to accelerate the reuse of these digital artifacts, and insofar as it permits scientists to feel like they're getting credit that they're owed. So yeah, that was my 2 cents on data and challenges around it. And I'm really happy to open the conversations and see what all of you have to say about it.
Super cool. I completely agree with you, Chris. Maybe there is a couple of things that I can add from my perspective. So actually, there is this really cool graph that I wanted to show you guys. I'm not sure if you can see it. Yeah. So here is a figure that shows you the total volume of data on the internet. And you see it's a non-linear, like accelerated growth path, right? So we had around 2 zettabytes of data on the internet in 2010. This year, it's supposed to be around 80 zettabytes, and it's supposed to increase even further to almost 200 in about 3 years from now. And the interesting thing is that we see a very, very similar trend in scientific data as well. So I've actually experienced that in my own research. So when we started to work on the genetic architecture of complex human behaviors, which was around 2008, 2009, the main problem that we had was really that there wasn't enough data out there to really identify super, super small effects of genes that they have on complex behaviors and complex outcomes in general, right? So there was a real break in the way that researchers were approaching that particular research topic. So before 2010, people were running what was called candidate gene studies. So they had a relatively small set of genes that they would test with very small samples, usually just a couple of dozens or hundreds at the very most, because it was extremely expensive to collect that data. And then what happened was that you ended up with the literature, the so-called candidate gene literature, which usually reported very, very large effects of these few candidate genes. And then there was a period where people started to replicate these results, and it turned out that they just didn't replicate, right? And we actually came into this trying to replicate some of the earlier findings with data sets that were in the order of maybe 10 or 50,000 observations, which was huge back in the days. It was like orders of magnitudes larger than what people had published earlier. And in our data sets, we just couldn't find any association whatsoever, simply because the effect sizes were so small that even with 50,000 people, you couldn't detect them. So there was this period in this research community where the insights started to sink in that the original candidate gene studies were just not robust, that we basically had to forget about them, like 95% or something like that, did not replicate. And then there was a couple of years where basically everybody was trying to do these genome-wide dissociation studies where you just look at all the genes in the human genome and you try to basically do a data mining exercise where you control for multiple testing, and you do that in very, very large data sets. But when people were doing that, they often came up like empty-handed, right? So they were running these studies and just nothing came out. For years and years, this was so incredibly frustrating. And at some point, the amount of data that was available was just large enough that all of a sudden results started to appear that were robust and that were replicable. So we went from 50,000 observations to 100,000 in 2013, and we went to 300,000 observations in 2016, and then to over 1 million in 2020. And now the latest version, so the latest generation of studies that I was involved in, they had sample sizes of up to 4 million people that were genotyped, right? So you see that there's this exponential increase in data availability. And in this particular case, it had something to do with technological progress. It was simply due to the fact that tremendous progress had been made in terms of genotyping. So genotyping technologies became cheaper and cheaper. And that just allowed all different sorts of people from around the globe to start collecting and analyzing that data. And so one of the things that we realized was that once we were at a point where we actually had results that were robust, there was tremendous value for us in making the summary statistics of our genome-wide dissociation studies publicly available. So they turn out to have a lot of use cases for follow-up studies, for comparisons, for, you can do stuff like genetic correlations, you can do biological annotation, you can use them for identifying causal effects under some assumptions. So there was a big demand in the scientific community for us to actually share that data. And it was actually, so what was really nice was that the summary statistics themselves, they were only, in the range of about 50 or 100 megabytes. So they're not really huge files. So we could just set up our own website put them there, and then anybody who wanted to use them, they could go there, they could download the data, and they could start working with it. And this actually generated a lot of citations for our underlying studies that published these summary statistics. And I think that's probably one of the main reasons why these studies ultimately ended up like literally with thousands of citations, simply because the data that we generated was useful. It was used by a lot of other people, and then they cited the original paper as an origin. But we would have run into problems if we would have had really, really large data sets, right? So if we would have had data sets in the range of terabytes or even petabytes, like it is the case in some fields of science, then we would have hit technological problems and also economic problems in terms of like how do you even pay for a storage provider? Where do you get the money from? So we had enormous support, luckily, through the Dutch supercomputer initiative called Surf-Sara. So that's like an infrastructure that all Dutch scientists can use. And we made very, very frequent use of that infrastructure, both in our analysis and in terms of like sharing data securely with our project partners. But even there, once we got to a point where we needed more than 100 terabytes of storage, it was reaching limits of what we could justify. So we needed to apply for grants specifically for the purpose of having that storage and compute facilities available to us. And then it was only available to us, and we could not share these resources easily with others. And what Chris has been talking about is actually a super, super elegant solution to all of these problems that is scalable and that relies on Web3 core technologies that have just been developed in the last couple of years, which is really, really cool. And maybe just another like tiny story about the incentives for scientists to actually share data. So Chris mentioned that some scientists are much more eager to share their data than others, and that there is big cultural differences and so on and so forth. And I can only like support that. So we've seen that over and over again in our genetics work. One of the things that is definitely playing a big role there in terms of the incentives is that the funding agencies that are sponsoring the collection of genetic data for a lot of these studies, they actually, in many cases, require you to make the data not publicly, but available to other scientists, right? So there's infrastructures that have been built for that. So for example, if you're financed by the National Institute of Health and you collect genetic data, then you're required to put that genetic data on an infrastructure called dbGaP, which they've set up especially for that purpose. And so people write these grants and they collect that data, and then yes, they put their data at some point on dbGaP. But we've seen a lot of cases that even researchers that have a funding requirement to actually share that data are not very eager to do that. So what we've seen in practice is that they found loopholes, how they can actually exploit the system to basically erect gates. So in theory, the data was available, but then you had a data committee that was looking at applications of people to use that data. And that committee was often run by people that originally ran the study, and they had no interest of actually sharing that data. So they actually denied a lot of the requests of people to use that data. Or what we've also seen is that people started sharing data that was ultimately not useful, right? So they ended up sharing summary statistics that contained a lot of data, but was missing other data that was absolutely crucially required for any other researcher to make use of it. So there was a lot of that going on. And again, I think that if we fix the incentives and we provide an infrastructure for actually doing that, for sharing that efficiently, we could make a lot of progress and move the needle, both in terms of scientific progress and replicability and openness. That's my 2 cents.
Yeah, and I think these types of data challenges, they will be facing more and more fields of science, as essentially, science is becoming more and more computational, and essentially data is constantly growing. we will start to stretch the limit of what's feasible on cloud infrastructure and these existing systems quite soon, actually. So I think this is also a momentous time to be building on these solutions.
Absolutely. So now is really like big data has been a term that I kept hearing on campus in the last couple of years. So it started becoming a topic of conversation in the academic community, at least in the community that I was active in, maybe around 2015. This is when this started to get traction. People started talking about it. And now it's a really big topic. So now a lot of people in my department and other departments, there is increasing like cases where people actually have access to really, really large data, or where they want to get access to a big data that already exists and where they're trying to figure out how they can make that work. So this is timely. It's part of, I guess, our evolution of science, that is just getting more and more computational and more data heavy over time.
I've got a question. Philip, when you were doing your work, how much time was spent collecting data and how much time was spent sort of doing work on that data?
So that's a great question. We in our project, so we actually did not collect the data at the individual level. So what we did was basically we identified groups of researchers that had already collected data that could be useful for our analysis, and we sent them an analysis plan, and they ran the analysis for us. They uploaded the results. We meta-analyzed the results, and then we did follow-up analysis, and we wrote papers with it. So we were not actually doing the raw primary data collection. The entire pipeline of what I was describing to you still took years for a group of maybe 5 to 10 core researchers who were working on these projects more or less around the clock. So there was a lot of like data processing, a lot of like organizational effort, and a lot of analysis and all that stuff. But I think this is probably dwarfed by the amount of effort that other researchers had previously invested into collecting that data. So that was, whenever you wanted to collect data, it meant that you needed to come up with a project proposal and then find funding to sponsor the data collection. Then you needed to do the actual data collection, and you needed to clean the data, and you needed to write a first paper that describes the data, make it publicly available, and so on and so forth. And in our case, in case of our research consortium, we were working together with over 100 research centers from around the globe, and they had each invested enormous amounts of time and energy and money, often in the millions or tens of millions, to collect those data. And those data were, then useful for a bunch of different purposes, including ours. But there were enormous efforts, and there are still enormous efforts ongoing in terms of collecting the data that was necessary for certain types of research.
It's really interesting. So the background to that question, I guess, or the larger question behind that is, like, as I'm listening to this new sort of evolution, as you described it, of how data might operate with new infrastructure, it makes me think of modular science, where you might have people whose only job is to collect data, and then you have people whose only job is to analyze that data. So there's the people who collect, the people who think about novel ways to use the new data. And that just seems like a more efficient way to do research, rather than someone who has an idea about something to explore spending like 5 years collecting data before they even get to start exploring their idea.
Totally.
It's really interesting.
100%. And I think, there is differences across scientific fields, but what I've seen, for example, in epidemiology, so we were working together with people in epidemiology at the Erasmus Medical Center, and they actually have one of the largest data gathering enterprises for epidemiology in the world, and there is exactly happening what you were describing, which is that they had so many people working on data collection and everything that had to do with it, that there was a specialization in labor. So you clearly had people that specialized in writing the grants to get the funding. Then you had people that specialized on actually collecting the data. They had they had an entire clinic actually set up to basically see patients and to collect these data. So they hired an entire staff of people that had no other role than to collect that data. And then you had people that were just cleaning that data and making it accessible to the researchers at the Erasmus Medical Center. And then you had the researchers themselves who were then analyzing and doing all sorts of stuff with that data. But there was a clear differentiation in job descriptions and stuff like that around this entire data collection enterprise, which it really was. It was like an industrial scale enterprise of just collecting data for science.
And then did they make it open? So something that pops into mind is
they did not. So
no, okay, great.
So
I'm trying to think of an example where giant open data sets like you're describing can be accessed by anyone. And the only in my ignorance, the only thing I can think of is the COVID projects.
There's a lot of examples where this actually works. So one of the best examples I can think of is the UK Biobank. So the UK Biobank is basically it's a sample of 500,000 British people that are all 40 years or higher, and it's based on a representative sample. And they have electronic health records. They've all been genotyped. They've all been seen in the clinic and examined. 100,000 of them are actually scanned, with MRI scans. It's really a countrywide data gathering enterprise, and it's sponsored largely by the British government and by the Wellcome Trust. And the people that are running that project, they made a decision very early on that they want to make all their data immediately available to any researcher, any bona fide researcher in the world. So they literally wanted to create an open database for science that maximizes the value of that resource for the entire world, right? And they did have big discussions about this at the beginning, but that's the route they took. It was enormously successful. So the UK Biobank is by far the most important data set for genetic research on a bunch of different diseases. And so many fantastic discoveries came out of that. They do have a data sharing model where after the first 5 or 6 years, where basically anybody could get that data for free, they now have a data program where basically anybody who wants to access the data has to pay basically an upfront fee. And then there is there's differences in how much you pay depending on how much data you actually need. So if you need the genetic data, you pay more. If you need the imaging data, you pay even more. So they have a model now to actually also collect some revenues from researchers around that. But what I've also seen in other cases, like at the Erasmus Medical Center, their incentive was totally different. So they did not make their data publicly available. And instead, you needed to have somebody at the Erasmus Medical Center that you were working with who gave you access to that data, or had a PhD student who could actually analyze the data. So it was very difficult to get access to it. And then they had this bizarre incentive model that they charged you 10,000 euros for each paper that you published on their data. Right. So it's a completely bizarre incentive, because all of a sudden you're like, okay, so I'm actually not supposed to make the best use of that data set in terms of discoveries, but I actually have to think really, really carefully now, for which project is it actually worth for me to put down 10,000 to work with that particular data set. And as a result, we often didn't use that data set for things that we could actually do for free with other data sets. So there's all this different sorts of stuff going on. But their incentive was clearly, they wanted to monetize this incredibly, valuable resource that they have created. But the incentive that they created were, let's say, far from perfect.
Hey, just to jump on that, that's a pretty cool incentive when it comes to prevent salami slicing of scientific results.
It's true. It did prevent that. Yes.
I know. It's actually a pretty solid one. It's like Well, if you're going to be paying every time you use that data set on a paper, you better make damn sure to make the best possible paper in the world, right?
Yeah, exactly. Well, yeah, you're right. I mean,
It's not bad when you think about it. I mean, it does incentivize limiting noise in the literature, right?
well, I mean, what it did in
Similar
our
to
case is simply that
submission fee. Yeah.
whenever we had a chance to use either their data set or a different data set that we could get through a different resource where we didn't have to pay for that, then obviously we did not use that. So,
Yeah, for sure.
This is crazy. So there's still many different ways this can happen, and there's something you said, Philip, that like you said they made the data open for bona fide researchers. I'm curious what your thoughts, you too, Chris, about like what the benefits can be if it's made open to anyone. And I'm thinking of just like pure open data where the public can come in and experiment with their own algorithms and their own ideas and how to use this data to get novel discoveries, new knowledge out there. And it lets people, from my perspective at least, get into the scientific system without having that huge capital cost of collecting data or paying to get access to a big data set, or even spending 8 to 10 years becoming a bona fide researcher to get access to the data set. I'm wondering if you guys think that's like of a benefit or sort of a drawback to the potential of the system we're building.
yeah, I mean, so in the case of genetic data, there is a lot of reason to be cautious about sharing that totally openly. I mean, first of all, there is legal restrictions, right? So there is like privacy concerns. So you actually have to verify and be able to track down who has access to that data for what purpose and for how long. So that data is just too sensitive. You cannot put it into the open domain. So that's one aspect. But then another reason why, at least in the case of genetic data, they never did that was because there was a lot of concern that once you start putting that type of sensitive data out there, even if it would be completely anonymized, that you would invite a bunch of like crazy people to start misusing that data to make all different sorts of crazy claims, right? So for example, you could imagine that somebody comes in with a malicious intent to show that people that don't have white skin have a lower IQ, and that this is due to different genes that they have, right? So these sorts of things, they have happened over and over and over again. And of course they're bullshit. And of course everybody who understands genetics understands that you cannot do these sorts of things, that they're not comparable. But once you open the floodgates and you allow all the crazy people to come in and to work with that data, without any doubt, there would be a bunch of like pseudoscience appearing that is just potentially really, really harmful. So this is why, at least in this particular case, they put gates around that, and they said, okay, so we want to know who is it that wants to work with that data and what is their intention, and we want to see what they actually did with the data. That is probably not going to be necessary for a lot of other fields of science, but at least in genetics, that was definitely something where people were rightfully concerned about.
Yeah, that makes sense. I mean, I could go into an hour debate with you about whether or not that sort of censorship authoritarian is good or not, but for another day, for sure.
Yeah. Totally. And
right.
just to be clear, so the type of censorship, it has been largely successful, but not 100%. So there is still a bunch of people that are out there with a malicious, ideological agenda that don't really care about whether the science is right or not. They just want to create the appearance that they've done something scientific to just basically underscore or illustrate their ideological claim. So that has still happened, and it has still caused a lot of harm, even though
as old as humanity itself. Yes.
Yes, right.
Yeah.
Alrighty. Well, I think we're getting to the last few minutes of the call. Wanted to go ahead and give anyone else who's here a quick chance to ask a question if they may have one. Ellie, Lorenzo, do y'all have anything that you want to know?
Yeah, I would like to ask a quick question to you guys. since my background is that I come from a residency trainee surgeon in orthopedics, I have the $1 million question. Since that an average orthopedic surgeon can't use properly a PC, how do you intend to incentivize surgeons, but in general researchers, to share their data, to open their data, to give a boost to future publications?
I love it. You're right. This is a $1 million question. Chris, you want to take that?
I know.
Well, I think at the end of the day, it's all about credit, right? It's all about feeling that you're being recognized for the service that you do to the scientific community, and that the people that matter to you recognize this, and that the funding agencies, institutions, and essentially sponsors of your research actually recognize your service to the community, right? So that's really the goal. So we have to create systems which makes it rewarding for people to share their data. And I think there's different ways to do this, different ways to go about it. Think of things that have been extraordinarily successful, that really appeals to our primal instincts as researchers, like attention trackers. For example, are you familiar with this little wheel that you have on many papers and many publisher websites, which tracks, Twitter mentions, all sorts of social media articles, blogs, articles in New York Times, all of this, right? Have you seen this?
No, personally not.
Yeah, it's called Altmetrics. And it's very, very successful because it's like, everyone wants to know what other people are saying about their research, right? Now,
Yes.
imagine if you had, some form of altmetric or some form of like attention tracker that essentially was like, hey, how useful are the artifacts that this person has posted in the open domain, and how much have these artifacts contributed to enriching the discourse and the discoveries in their communities, right? So I think that's really the key. It's like we have to create salient markers of credit, and these salient markers of credit need to be recognized for what they are, because essentially they're like sharing your data ahead of you using that data to publish a discovery, essentially giant opportunity cost, right? So if we want to incentivize that, we have to make it, to make it rewarding and salient for researchers that create these knowledge public goods and these data public goods for others to work on. So we need to find affordances that provide them with transparent credit attribution, that makes them celebrated by the community for doing the right things and contributing for public good, that attracts the attentions of funders who might be more willing to fund future research, future data collection endeavors. And so, yeah, it has to be a combination of all of this, essentially.
Yeah, thank you. This altmetric site, it's amazing. I've never heard of it, so I will explore it more. And then think that, as I told Eric a few weeks ago, I was at a congress of the official Italian Congress of Orthopedic Surgeon, and I talked to one of the orthopedic researchers that was developing an AI based on X-rays of orthopedic patients. And the most interesting thing for me is that when those kind of researchers talk you about big data and data science, and when you approach those kind of researcher and you kind of ask them, how do you plan to exactly use those data? How do you plan to integrate and share those data? And this is the part in which we as a community kind of hop on. We must try to train those kind of researchers and give them the tools. And this is for me the difficult part, the most difficult part. And we need a strong community for that, because it's the main obstacle for me, at least.
Oh yeah, definitely. I mean, education plays a tremendous role in all of this. And, to reduce the cost of education, we have to make simpler tools to use, right? So these things kind of come hand by hand. And I think if we're able to make simple tools that facilitate sharing data between researchers, then we can reduce the burden of education by essentially making it simpler to access, to use, and to essentially benefit from.
Yeah.
Alrighty. Well, with that, I think we are closing in on the end of the call. We're a couple minutes over. So thank you everyone for joining. Feel free to come back next week. And Coffee House starts now.
Thank you all.
Thank
See
you,
you.
everyone.
Thank
Ciao.
you.